All right, this video is going to go over our next probability lesson. This is section 5.2, part of 5.3 in your textbook. And on the handout, it'll be pages 9 through 14. Let's get started. So today we're going to be trying to look at two-way tables, Venn diagrams, and apply some general formulas for probabilities and determine if two probabilities are independent of each other. And we'll talk about what all that means coming up. For starters, let's talk about the word or. And or, when you're asked, when you think of the word or, you mean this or the other. Like, for instance, if you're at Applebee's, you want fries or onion rings, you can't just get both of them, right? You're going to have one or the other unless you want to pay for both. At Starbucks, if you're offered whipped cream or sprinkles, you can probably get both of them for, the same price. It's just usually they offer that kind of stuff on their specialty drinks without charging extra. I don't know. But in statistics, we use the Starbucks version. So like, or in our case means this or that or both. So think about that as we go through our definition. So let's start with a classic Venn diagram. In the context of statistics, or in our case means only A plus only B plus what's in the middle. So we think about like left Pac-Man, right Pac-Man, and football. So you can see that scenario here, left Pac-Man, right Pac-Man, and football combined to give you the entire package, A or B, or both. So look at the Venn diagram below. We want to know what's the probability of only event B. Well, that's going to be 0.2. That's the right Pac-Man. Only a probability of events A and B, and is that overlap in the middle. So that's going to be the football. That's 0.3. And the last one, probability of A or B, is going to be all three of those, 0.4, 0.3, 0.2 added together, which is going to give you 0.9. Notice there's a little bit left over. Well, that's going to be 100%, because not everything in probability land is going to fall in those Venn diagrams. Sometimes there'll be things outside of it. So that's where the remaining is. And if you do the math, they all add to 1. So let's talk about a thing that I can do one of these things. I can raise my eyebrow, but I cannot roll my tongue. So think about what you can do. We're going to take some class data, but for now we're going to just use some made-up data to make this stuff make sense. If you're watching the video and you weren't in class, you can just use our made-up data here. In class, we'll combine our class. We have a small class, so we're probably going to go next door and get their data too, and combine our efforts. So here's some made-up data here. Let's assume that our real class data is going to be different. So it might be a little bit off, but for right now, we're going to say, all right, well, there are some people that can evil eyebrow and roll their tongue. Some that can only do the evil eyebrow, but they can't roll the tongue. So I'd be in this group here. But together, they combine to all the possibilities of evil eyebrow. And the same thing with the not evil eyebrow. There's some that can't do their eyebrow thing, but they can roll their tongue. Some that can't do either one of them. And together we can get our totals, fill out a Venn diagram, and do some math with that. So here is our Venn diagram of our made up data. So let's talk about the first question here. Suppose we randomly chose a student from the class. Find the following probabilities. Let's start with the yes TR. Well, we can see here that either from the Venn diagram or from the table itself, there are 19 people that can roll their tongue, including the ones that can do the evil eyebrow and cannot do the evil eyebrow. So on the Venn diagram, you can see it's that overlap, the football plus the left Pac-Man, 14 and 5 give you 19, and they come from here. So 19 out of 30. What about yes or no tongue roll? Well, the remainder is going to be 11 out of 30. There are going to be 11 out of those 30 that can't tongue roll. So 19 can, 11 can't. Together, that give you combined 30 out of 30. Same thing with the evil eyebrow. We can look at the 8 that can do the evil eyebrow, including the 3 and 5 here. That means that the remainder is going to be 22. These 14 plus the 8 that can't do either combined are going to give you 22. And again, those are going to give you a whole 30 units. Then you can go your individual cells. So TR and yes TR and yes TE, well, that's going to be 5 out of 30. Yes EE and no TR, that's 3 out of 30. Yes TR, no EE, 14 out of 30. And finally, no to both, 8 out of 30. Whether you use a table or Venn diagram, you can get those probabilities. So now let's take a look at choosing a random student from the class. Let's find some probabilities. The probability of yes EE, we did that before. That's going to be 8 out of 30. The probability of no EE, no evil eyebrow, that's the 22, the remainder out of 30. And notice that those both give you 1. They add to 1. There is no overlap. These 5 and 3 are separate from these 14 and 8. So that means these guys are what we call mutually exclusive, and their probabilities, the or, A or B, is simply their sum. 8 out of 30 plus 22 out of 30 is 30 out of 30, which is 100% 1. They can't happen at the same time. There is no overlap. Now let's look at a different scenario. Suppose we want to find the probability of, yes, they can roll their tongue. Well, we know that's going to be 19 out of 30. Those 14 and 5 together give you 19. What's the probability they can do evil eyebrow? Well, we got that before. That was 8 out of 30. But notice here there's some overlap. So the probability of yes to both, one or the other, is not just 19 plus 8. We got to take away that one we haven't counted because we don't want to count it twice. If I did 14 plus 5 plus 5 plus 3, I'm counting that 5 twice. So we're going to subtract one of those 5s out, and that's going to give you 22 out of 30. These are what we say, if you do the individual cells, 5 plus 3 plus 14, that's also going to give you 8 plus 14, which is 22. So you can get it that way too. But the important thing is these are not mutually exclusive. And since they're not mutually exclusive, there can be some overlap. So what we want to do is, in this case here, we want to add their probabilities together, but we want to subtract that overlap here, that what they have in common from the 2 overall probabilities. Okay, so next, suppose we randomly chose a student from class, given that the person selected is yes evil eyebrow. What is the probability that they are a yes tongue roll? So in this case here, we want to only look at the evil eyebrows. And you can see, well, there's only 8 that can do the evil eyebrow. But out of those, 5 can do the tongue roll. So that little vertical bar means given. Only out of those numbers. So we say, well, 5 out of 8, 62.5%. That's the probability here. Now, let's look at the next question. Given that the person selected is no evil eyebrow, so out of these ones, what's the probability they are a yes tongue roll? Well, think about what that is. That's 14 out of 22. That's a little bit different, 63.6%. So those aren't exactly the same. They're a little bit off, but you can see the breakdowns from our made-up data here. These are what we call conditional probabilities. The condition is given in the denominator of the calculation. So we don't use the entire total in these cases. We use just like the margins. And that's for our conditions. So the definition for independence is if knowing whether or not one event has occurred, then the probabilities would not change. That would be considered to be independent. So in this situation here, let's talk about tongue roll and evil eyebrow. Well, those 2 probabilities, because knowing that the evil eyebrow was whether students could do the evil eyebrow or not, notice those changed a little bit. So because those weren't exactly the same, we'd say these are not independent. Based on our data, people who can evil eyebrow are less likely to be able to roll their tongues. Now it's close, but again, they have to be exactly the same for them to be independent. And so they're not going to be independent in this case. In other words, knowing whether someone can evil eyebrow changes the probability they can roll their tongue. So let's look at some data from a high school in Michigan. I'm from Michigan, yay. We have a breakdown, 600 seniors at the school. Here are the ones that can do the evil eyebrow, no evil eyebrow, tongue roll, no tongue roll, and all the totals. Let's find each of the probabilities. You can pause the video, try them on your own. Probability of a tongue roll, that's going to be 480 out of 600, so that's 80%. What about yes TR given yes evil eyebrow? Well, evil eyebrows are here, so it's going to be 180 out of 200, 90%. Yes tongue roll given no evil eyebrow, 300 out of 400, 75%. Notice those are different. So that means they're not going to be independent. Knowing whether someone can evil eyebrow changes those probabilities. Now, let's pretend they're independent. Okay, let's erase all the individual numbers here and let's make up our own numbers just for the sake of proving what independence means. From each of the following, we can use the independent rule. What we're going to say is if they are independent, the probability of tongue roll, sorry, TR, should be the same for students who evil eyebrow and who cannot evil eyebrow. In this case, they should all be 80%. So what's 80% of 400? What's 80% of 200? Those should be the same for them to be independent of each other. So you can do some quick math, and that's going to give you 160 for yes tongue roll and evil eyebrow. And for the yes tongue roll, no evil eyebrow, that should be 80% of 400. So it should be 320. Which means that if you do some subtraction, this should give you 40 and this should give you 80. So now let's find some probabilities. The probability of yes tongue roll, well, we got that before. That's 480 out of 600, that's 80%. Yes tongue roll given yes evil eyebrow, that's 160 out of 200, that's also 80%. And yes tongue roll given no evil eyebrow, again 80%, because we manipulated the numbers in the table to give you that. So this is a scenario where you would see, well, if those were giving you the same percentages, they would be independent of each other. So what do you notice about the answers to 9 and 11? Well, number 9, they're different. Number 11, they're the same. Let's generalize. If events are independent of each other, then the probability of one event happening should be the same as that probability of the event happening given something else and given that other thing not happening. Those should all be the same. And so in our situation here, these are independent with our made up numbers because you got the same probability for all of those. So probability of A stays the same whether or not B happens. B does not impact the probability of A. So let's go over some important ideas. In a two-way table and Venn diagram, you can kind of lay out the same data. Looks a little bit different, but you can see here the overlap typically is the yes for both. The not for one, but the yes for the other is one of the Pac-Man. So in this case here, the left Pac-Man, this 2, is yes A but not B. And then the right Pac-Man, the 3, is yes B but not A. And then of course there's always going to be some left over on the outside, and that's the not for both of them. The or simply means addition. And statistics means only A or only B or both. Okay, you could include both. That's that middle football there. And the general rule for or is you want to add their probabilities together, but subtract the overlap. Now, in the case of mutually exclusive, there is no overlap. So we don't have to do any subtraction. We simply just say probability of A plus probability of B. But you got to know they're mutually exclusive before you can do that. So either you've been told, or you find out that the overlap is 0 and you subtract 0. Conditional probability is always going to be the overlap out of the given. So like in this case here, if I want to know the probability of A given B, well, that's going to be the overlap out of the B's, since we're given B. And if I want to know the probability of B given A, I'm still going to use that same overlap, but I'm going to do it out of the total for the A since I'm given it. So the order matters in these. Independent probabilities, when knowing one event has occurred or has not occurred, does not affect the probability of the second event. So you want to know independent probabilities that the probability of one event is equal to the probability of that event given something else happens. which is also equal to the probability of that event given the complement of that happens. So all three of those should be the same in order for them to be independent. Now there is an independent rule. I'm gonna go back here and show you what that means a little bit. Okay, I wanted to pull up the data from our table where we filled in those numbers to make them independent. The rule for independence is if you multiply the individual probabilities, so the probability of one thing happening times the probability of the other thing happening, then that product should be equal to the probability of that overlap. So let's look at the table for an example. The probability of yes tongue roll is 480 out of 600. Now we had gotten that before, that's 80%. The probability of yes evil eyebrow is 200 out of 600, which is a third. Now, if you times those two numbers together, let's do that real quick. 0.8 times, I'll just do times 1/3 since we know that that does reduce. That gives you 0.266 repeating. Now, look at the probability of yes to both. That's 160 out of 600. It's the same. That happens for independent you can verify it using some quick math, but take my word for it. When they're independent of each other, the overall probabilities will multiply to their and probabilities. So that's another way to check too. Let's talk about notation. You're going to see some formulas in your textbook and on formula sheets. And it's going to see symbols like this U and this upside down U. And A or B, think about or being union, okay? Combined U. Think about and being intersection. And also think about the that middle letter for and, it's kind of a lowercase n, so you can see that there, it's going to be intersection. So or doesn't have a U, but union is or, n is intersection. If you see that little C in the exponent, that's really just a complement, it's the not. So subtract from 1. And then A given B is a vertical line B. So you have a check your understanding, a couple questions here. Pause the video, try it on your own, and you can unpause it and you can see my explanations. Okay, so for number 1, a random sample of high school students were surveyed regarding their toilet paper habits. Personally, I like to have the paper in front. Should the toilet paper pull over the roll? Do they replace the roll when it is empty? I like to think I do most of the time. The two-way table displays the data. Suppose we chose a member of the sample at random. Define events O, over, and R, replace. Okay, letter A. Explain in plain language what POC means and find the probability. Well, that means, well, let's get our totals first. That helps. So if you aren't given totals, quickly do that. Add them onto your margins so you have them. Now let's answer the question. It's the probability of choosing a student who does not prefer toilet paper to pull over the roll. So not over. So look at the overs here. Toilet paper to pull over the roll. These are the yes, so that means these are the nots. And because it's the entire thing, it's not a conditional, it's going to be 46 out of 116. Or 24 plus 22 out of 116. If you weren't given those, you had to add those to get the 46. That's the not. Now let's look at the part B. Explain why P, O, or R is not simply equal to PO plus PR. Then find P, O, or R. Well, the probability of O is 70 out of 116. Probability of R is 82 out of 116. But notice that these are not mutually exclusive, meaning there is some overlap here, right? We got this 58 hanging out. Well, what do we do with that 58? Got to take that away. It's being double counted when you add those together. So if you do 70 out of 116 and 82 out of 116, add them together, great. But take away that overlap to get your actual probability. Because if you add 70 and 82, That's going to be 152, which is more than the total amount of people surveyed. That doesn't even make sense in this situation. So you got to subtract the overlap. Let's make a Venn diagram. These should be the numbers: 12 for over but not replace, 58 for both, 24 for replaces but not over, and then 22 that apparently they don't do any one of them. That's kind of weird. Let's see. Okay, letter D. So what is the event does not replace, write the event does not replace the roll and prefers the toilet paper, pulls over the roll in symbolic form. And intersection, like upside down U. So what we're going to say is, think about your Venn diagram too. This is this left Pac-Man here, right? It's the does not replace the roll. So here's the replace the roll, 58. So the does not is the 12. And O is over. So that's going to be the, well, that's going to be this column here, but we're looking for the intersection, right? So it's going to be 12 because that's where they meet together out of 116. All right, try this one, pause the video. Okay, for this question here, pause the video again, try it on your own, read through the questions and unpause it and check with me. All right, question number 1. The Pew Research, or question 2, the Pew Research Center randomly selected 100 mothers of age 40 to 44 in 1976, 1994, and 2014, and asked each mother how many children they have. Two-way table summarizes their responses. Suppose we randomly select one of the survey respondents. Define events C, have 4 or more children, S, 1976, N, 1994, and F, 2014. First question, find P, C given S, interpret this value in context. C given S is talking about the probability of having 4 or more children given 1976. So again, given 1976. So we're only talking about those. So what does that mean? Well, we're only talking about the 100 people from the 1976 poll. And out of those, 40 had 4 or more children. So 40 out of 100 is 0.4. So the interpretation being, given that the mother was surveyed in 1976, there is a 40% probability that she had 4+ children. Part B. Given that the chosen mother was not surveyed in 1976, what's the probability that she has 4 or more children? Write your answers a probability statement using correct symbols for the events. So these are the other ones, right? These are the 13 and 13 from 1994 and 2014 respectively, out of the 200 combined, right? These are the not 1976. So we're talking about 94 and 2014. Here's a symbolic notation, P, C given S, complement of C, so of S, so the not 1976. So that's going to be 26 out of 200, which is 0.13. Or C, are the events surveyed in 1976 and 4 or more children independent? Well, in other words, is 66 out of 360 the same as 26 out of 200, the same as 40 out of 100? Are those the same? They're not. 66 out of 300 is only 0.22. Probability of just 4 more children, totals. Probability from the previous ones, the 4+ children out of the 1976, and the probability of 4+ children out of the other years, those are all different, right? 22%, 40%, 13%. So they're not independent. So you can say the events surveyed in 1976 and 4 more children are not independent because mothers surveyed in 1976 are more likely, 40%, to have 4 children than the mothers not surveyed in 1976, 13%. If they were independent, they'd be exactly the same. And that's it. Thanks for watching. Hope this was helpful.